Consider this list of numbers: 1, 8, 15, 22, 29. I want us to list the next three numbers in this list of numbers. So that would be 36. I'm sure you're thinking 43 and 50. Okay? All right. So let's get a formula for this list of numbers. Let's assume this list of numbers, we name them A. So call this A1, this A2, A3, and so forth, A4, etc. Okay. So if we let A1 be 1, and we let A2 be 8, we can get a formula. We can get an explicit formula. So what do I mean by an explicit formula? I can get explicit formula. So that would be AN is equal to 1 plus 7 times something. So let's think about it. A2 is 1 plus 7. A3 is 1 plus 7 plus 7. That's 1 plus 2 times 7. A4 is 1 plus 7 plus 7 plus 7. So that's 1 plus 3 times 7. So this is 1 plus n minus 1 times 7. So that's our formula. That's an explicit formula. So an n goes from 1 to infinity and so forth. We can also get what we call a recurrence formula. Or recurrence relation. Recurrence relation just means that we're writing one term in terms of the other. So what does that mean? So if we have the term an, then what this means is that we can, to get an plus 1, we just have to add 7 to our an, right? Or we begin, so I'm going to, instead of writing an here, so I'm going to say an plus 1 is an plus 7. Okay. So because a2 is a1 plus 7, a3 is a2 plus 7, etc. And n still goes from maybe n this time will go from 0, and so forth, so that a0 will be 1 in this case, and so forth. Okay, so we can talk about limits. Let's talk about the limit of this list of numbers. Okay, so we have an explicit formula and we have a recurrence relation. So we can compute the limit by just even looking at the list of numbers. So as n goes to infinity, what does this list tend to? So we can do this also by just looking at our explicit formula. So limit as n goes to infinity, or let's just say, let me write it this way. As n goes to infinity, if you take this, the explicit formula, you see that an goes to infinity also. Okay, So I have a list of numbers, and I can compute a formula for generating the numbers, and I can find a limit, try to compute the limit of the numbers, and so forth. So this must be an interesting and useful concept. So this is the concept of sequences. Any list of numbers actually is a sequence of numbers. And I'm sure you've used the term sequence before. It's not necessarily a mathematical term. A sequence is just it's a term that everybody in every field uses. But when it comes to mathematics, when you say the word sequence, there are a lot of operations involved in sequence. There's a lot of operations. There are a lot of well-studied formulations and well-studied characteristics of different kind of sequences. So this is an example of a sequence. So an example of a sequence. So maybe we can formally define what a sequence is now with all these things we've done. So definitions. So a sequence. So we're going to represent it now as ANs. All right. So our AN is from n from 1 to infinity, or simply AN is an ordered list of numbers of the form A1, A2, A3, etc. So it's just a set of numbers that is ordered. So a sequence may be generated by an explicit formula of the form AN is equal to f of n. So think about what we had here. So this is our AN over here, and this is the f of n, a function of n. For n equals 1, 2, 3, and so forth. Okay. A sequence may also be generated by a recurrence relation. Of the form AN plus 1 is equal to f of AN, where A1 or A0 is given. All right, so we have the recurrence relation here. So this is AN plus 1 over here, and this is our f of AN. All right. Now we can compute limits. We already did. if the limit as n goes to infinity of an is equal to L, we say that the sequence an converges to L, right? If no such L exists, we say that our sequence diverges. Okay. All right, let's look at another sequence. Let's look at a second example sequence. So, let's just call this more examples. First example, let's have our sequence 1/2, 2/3, 3/4, 4/5. It's a nice little sequence. All right. So we can definitely look at the next three terms like we did before. 5/6, 6/7, 7/8, etc. And then we have an explicit formula. An explicit formula would be an is equal to n over n plus 1. All right, so a1 is 1 over 1 plus 1, which is 1 over 2. a2 is 2 over 2 plus 1, which is 2 over 3, etc. All right, so one thing we can actually do is we can actually sketch a graph of any sequence. It's more of like a discrete graph. It's not like it's not continuous. So this is n when n is 1, when n is 2, when n is 3, when n is 4, and so forth. Where n is 1, our function is 1/2. The value is 1/2. So we get something like this. When n is 2, it's 2/3. So you get here. When n is 3, is 3/4. When n is 4, is 4/5, and so forth. So you just get a graph that keeps going and going and going and going. And of course, this point is 1 over here. So you just get dotted lines, okay? All right, so if you want to join this, you don't have to join it, but I just want to show you the trend. Let me try to join it, but normally we don't join it. I'm going to delete all this, okay? So, but that's how it keeps going, and it seems like it has a horizontal asymptote over here at 1. That's a horizontal asymptote. So with this, we can actually see that the limit as n goes to infinity of an is the limit as n goes to infinity of n over n plus 1. If you remember your limits very well, you know that this is just equal to 1, right? And you don't have to do a whole lot. You can just look at it and see that it's 1. But if you want to do more, you can rewrite this as limit as n goes to infinity and divide the top and the bottom by n. So if you divide the top by n, you get 1. The bottom, you get 1 plus 1 over n. And as n goes to infinity, this just goes to 0. So you're left with 1 over 1. So that's 1 over 1. All right. Let's do a bunch of other examples. Let's look at some formulas for sequence. So So let's look at 2. I want to write down the first 4 terms of each sequence. Okay, so we have, say an is 1/2 to the power of n. 1/2 to the power of n. Or actually, I want to write it this way. Yeah, we can write it this way. 1/2 to the power of n. But know that this is the same thing as 1/2 all to the power of n. Okay. This is an example of a geometric series. We're going to return to geometric series, but this is an example of a geometric series. And geometric series usually have the form, oh no, what am I saying? Geometric sequence, not series. So geometric sequence usually has the form an is equal to r to the power of n. So in this case, our r is 1/2. But we'll come back to this. So let's write the first 4 terms. The first 4 terms, if n is 1, so we get 1/2. a1 is 1/2. a1 is 1/2. a2 is 1/4. a3 is 1/8, and so forth. And you can see that the limit as n goes to infinity of an is actually 0. So if you plot the graph of this, and let this be 1. a1 is that, a2 is 1/4, a3 is 1/8, a4 would be 1/16. So if you look at the trend, maybe you want to join them, but usually the graph of a sequence, you don't join them. But for the sake of visualization, let's try to join them. Oh, what did I just do? This is n, right? And this is an. Okay, let's look at another sequence. Okay. So let's look at an. An is -1 to the power of n times n over n squared plus 1. Okay. So a1 is, just plug 1 in for n. If you plug 1 in for n, you get -1/2. a2 is going to be 2/5. a3 is going to be -3/10. a4 is 4/17. Okay. If you look at this looks like it's going between negative and positive. But let's try to sketch it. Let's try to plot the points. This is 1. Let's do 1 here, 2 there, 3, 4. Let's see how it's going. And maybe 5. So this is, let's put 1/2 here. And then let's put -1/2. When n is 1, 1, 2, 3, 4, 5. When n is 1, you get -1/2. When n is 2, it's 2/5. 2/5 is smaller than 1/2, so it's somewhere there. When n is 3, it's -3/10. 3/10 is like almost like 1/3. So it's just gonna be maybe somewhere here. So you can see the pattern now. And A4 is 4/17, which is like 1/4. Close to 1/4, not like 1/4. So it just keeps coming close and close and coming close and close. So at the end, if you try to join this, look at what you get. Again, we don't join the points for sequences because they're discrete points. But for the sake of visualization, see what's happening. So we can imagine it's coming like this. Okay. So this can tell you, can show you that the limit as n goes to infinity, you can calculate it using this formula. Remember how to calculate limits from Calc 1. If you let n go to infinity and you use the methods for Calc 1, this actually goes to 0. And our graph shows that it goes to 0. All right. So okay. So I want to do more examples. Let's call this number 3. Let's go back to the same kind of examples we did before. We want to find an explicit formula. Explicit formula or a recurrence relation for each sequence. So the first one, we have this sequence 3, 6, 12, 24, 48, etc. So let's see what's going on. A1 is 3. A1 is 3. A2 is 2 times 3. A3 is 2 times A2. So are you seeing what I'm seeing? You have A1, but A2 is 2 times A1. A3 is 2 times A2, which is 2 times 2 times A1. A4 is 2 times A3, which is 2 times 2 times 2 times A1. I think we get a pattern here. We get that this is 2A1 and A3 is 2 squared A1 and A4 is 2 cubed A1. So we can say that AN is 2 to the power of n minus 1, I think, A1, but A1 is 3. So this is just 2 to the power of n minus 1 times 3. I bet you there are other ways to write this. So our formula an, our answer will be an is 2 to the power of n minus 1 times 3. And then this is for n starting with 1, 2, 3, etc. n starting with 1, starting at 1. But then if we decide, oh, how about we make this a0? Let's start with 0, a0, a1, a2, a3, etc. Then our formula, we can write our formula. I'm going to write it in black. Our formula can also be 3 or 2 to the power of n times 3, or 3 times 2 to the power of n. I don't know why I had 2 to the power of n for n minus 1 first, but this is when you start with 0 and go 1 and 3. So we can start our sequence with any group, any subscript we want. We can start with 0, but it's usually customary to start with 1. Sometimes it's usually easier, let's put it that way. So this is an explicit formulation, or explicit formula. So how about a recurrence relation? So we can just, recurrence relation is actually easy. You can just say an plus 1 is equal to 3 times 2. What am I doing? It's just 2 times an, right? For n starting with starting at 1, 2, 3, going. But if you, whenever you have a recurrence relation, you always have to define the initial term. In this case, our a1 is 3. All right. Let's try another one. Let us try another one. B. All right. Abi, so how about this sequence? How about 64, 32, 16, and so forth? So you get it. You will see that an, let's only just do an explicit formula here. Right? A1, you have A1. A2 is 1/2 A1. A3 is 1/2 A2. So we can see that an, or let's do what we did the other time. So we can say A1 or A2 is 1/2 A1, and then A3 is 1/2 A2, which is 1/2 times 1/2 A1, so that an is 1/2 to the power of n minus 1 A1. So that's our formula. An is 1/2 n minus 1 A1. But A1 is what? A1 is 64. All right, you can write it as 64 times 1 to the 1 over n, 1 over 2 to the power of n minus 1. Okay, let's try another one. let's do something that's okay. How about this? We have 1, -2, 4, -8, 16, and so forth. All right. So let's go for an explicit formula. Okay. So this is A1, A2, A3, A4. But look at this. A1 or A2. Let's start with A2. A2 is -1 times A1. All right. A3 is -1 times A2, which is -1 times -1 times A1. All right. Are you getting this? So, no. I screwed up. I'm rushing. Why am I rushing? So this is, sorry, -1, -1 times 2 times A1. That's what I meant. Now look at A, that's A3. No. Pardon me. Let me fix my things over here. All right, start with A2. A2 is -1 times 2 times A1. Because A1 is 1, this just gives you -2. But now check this out. A3 is -1 times 2 times A2, which is -1 times -1, or -1 times 2 times A2, which is -1 times 2 times A1. So you end up with -1 to the power of 2, right, times 2 to the power of 2 times A1, which is 1. So in general, I think we get the idea now, and we've had a lot of practice on this. So our AN is -1 to the power of n minus 1 times 2 to the power of n minus 1. So that's what we get. Of course, the recurrence relation is just easy. We forgot about that. The recurrence relation is just going to be A1 is 1, but then after that, AN plus 1 is -2 times AN. All right. Okay, what else can we do? Let's talk a little bit about series, all right? An infinite series. So an infinite series is the summation of every term in a sequence. And the notation is usually this. So you have all the terms in the sequence. You have say you have the terms. The terms are A1 plus A2 plus A3 and so forth. You add everything to up to infinity. You get, this is the notation. The notation you get is this. Notation. Or the notation we use is this. You have an, you're summing all the an's, summing all of them. This is called the sigma notation. You're summing all the an's and going from 1 to infinity. So this is what we call an infinite series. This right here is called an infinite series. Okay. But now, assuming you don't want to sum everything, you just want to sum from you don't want to sum everything. Let's say we sum from 1, A1, A2, A3, maybe to some an. Let's assume n is 10, say A10 or an, where n is 10, capital N. All right. So this would be summation n from 1 to capital N. Now this is called a partial sum. A partial sum of the series. Partial sum of an infinite series. Okay. Well, let me make maybe I should make a definition. I always like to make a definition. Okay, so let me put it here. Another definition. The partial sum of an infinite series. Is just a truncation of the terms well, of the terms that add up to form the series. Okay, so this is probably not a very precise definition, let's put it that way, but it gets the job done. So an example would be that. Okay. Now, let's do some examples and then we stop there. So if I have, let's do some examples. The first one, assuming I have this series, I have let's get a series. Oh, we have a bunch of series over here. Why am I acting like I don't have series? I've got series for days. Okay, so we have that. Okay, so this series 3, 6, 12, 24, 48, and so forth. So this series we can talk about the sequence. So the sequence, we know that the formula for the sequence is an is equal to what is it again? 3 times 2 to the power of n minus 1. Then the series will become summation n from 1 to infinity of an, or we can actually write it as summation from n to infinity of 3 times 2 to the power of n minus 1. Whatever you feel like. But I think we should stick to sequences for now. We'll come back and do a full video on series, okay? All right. But this introduction should do. I will see you in class